So, good morning all. It's a pleasure to me to introduce you Maria Lugaro. And she is actually a Momentum project leader of the Academy of Science in Hungary at the Konkoly Observatory. And she did several postdoctoral stays, one in Cambridge, another one in Utrecht, and other one at the Monash University in Melbourne, Australia. And her research interests are mainly stellar nucleosynthesis and how to interpret the abundances that we see in meteorites and stars, as well as star-star grains. And also she's very interested in the radioactivity signatures in meteorites. So today she's going to talk about the last asymptotic giant branch star that contributed to our solar system. So.
I don't want to spoil the end of the talk, so I will not explain in detail now what I mean by the last asymptotic giant branch star, because that's what we will try to find out. And also I will not introduce my co-authors here, because you will see more of them during the talk. Okay, so because this work is basically based on using radioactivity as a clock, as a chronometer to measure times in the cosmos, I thought I'd start with a brief introduction, with a brief reminder of what is radioactivity, and this is quite easy for me because radioactivity is really quick to explain. It's very simple. So here is the law of radioactivity. As you see, it's very quick to write. So N is the number of radioactive nuclei, and the rate at which these radioactive nuclei decay with time, so dN over the T, is simply proportional to the abundance itself of these nuclei. And the constant of proportionality is this lambda, which we call the decay rate. Of course, there's a minus here because these nuclei decay into something else. So the abundance will decrease with time. The nice thing is that this decay rate is constant. It doesn't change with time. So it is extremely easy to integrate this equation. And if you do that, you derive this very simple formula that relates the abundances of radioactive nucleus at times T1 and T0. This one I call N1 and the NN0, directly to the difference between the times T1 and T0. You just have to take the logarithm of the abundances, you multiply it by tau, which is nothing else than the inverse of this decay rate, and it's called mean life, and then you get directly this time interval. So you can see it's extremely powerful. It is a very precise clock. All we have to know is this tau. In principle, we know tau because it can be derived from nuclear experiments. So this is a known quantity for each nucleus that we're studying, but I have to put a warning that the nuclei I'm looking at, they have a half-life that is of the order of like millions of years. So often it's not easy to actually derive this quantity because you see something that changes of the order of millions of years. So you have to count something that happens very slowly. But in principle, we have good derivation of this quantity, but sometimes we have some surprises. So what are the times that we are interested? What time we can try to measure? The time I'm interested in are related to the birth of the sun. So it is kind of natural to set this T0, one of this time, to the time when the sun was born. This is not the only reason why we choose T0 as the birth of the sun. The other reason is that we have N0. So N0 is the quantity that we need to use the formula that I showed you before. And these N0 are available because they can be derived from the analysis of meteorites. Okay, so we have very strict constraints on N0, so this is a good starting point. This is a list which is not extensive, is not the complete list, it's just to give you some example of what are these radioactive nuclei for which we can derive the abundances at the time of the birth of the sun. I put here some of the more interesting examples. As I said, the list is maybe twice as long, but these are interesting because it already shows how much variety we have in these nuclei. So we have both nuclei that are quite light. So the 26 aluminum, for example, its mass is quite low. But then we go to nuclei like curium 247, so this is extremely heavy. And then they also vary a lot in terms of their half-life. For example, we have nuclei that decay of the order of 100,000 years. This is a quite short decay rate. But then we have nuclei that decay in like 22 million years. So with these nuclei, we can actually try to investigate different time intervals, because of course they can give us sensitivity to different time intervals. And then also we have a huge variety in how well we know how much it was there in the early solar system. For example, we have nuclei like this one, the aluminum-26. The early solar system abundance is always reported with respect to a stable nucleus, so this is always the ratio of 26/27. Is given, we did an uncertainty of 2.5%. It is extremely well studied. It was the first to be discovered in the 70s. And so this is giving me a really strong constraint. There's other nuclei that are as well known, for example, this manganese 53, which is now within 10%. Hafnium 182 is now well within 4%. And then we go to other situations where, well, we know that these nuclei were there, but we're not 100% sure on the right number to put here. For example, for this palladium 107, there's a 40% uncertainty. And then, unfortunately, there are some cases that, again, we are sure they were present, but people doing the experiments, they find different values depending on which rocks they use, depending on which instrument they use. So for some of these, they are crucial. But for example, ion 60, you see there's a 3 order of magnitude difference depending on which studies you look at. So this one would be good to have a good number, but we're still working towards it. So if I go back to use the law that I showed you before, I need a T0, and I want to measure the difference between T0 and a certain T1. So what do I choose for T1? There are two things that we can do. We can, of course, go forward in time. And this has been done extensively. So it has been done to the point that we can actually derive a detailed chronology of the growth of planet in the solar system. If you're interested in this topic, this is not my field, but there's a very good review from 2011. Here I just put one famous example. We have these chondrules that are little droplets of melted rocks that are found in most meteorites. And it's still not that clear how they formed, but thanks to using this clock, it could be measured that they formed about 1 million years after the birth of the sun. It's just one example. But what I was interested in was to try to go backward. Okay, so can we go backward in time and try to derive something about the prehistory, as I would call it, of the sun, of the matter that ended up in the solar system that we have today? So what can we do? Can we define some time T1 that we can try to measure using these clocks? So there are two different times that we have identified that we can measure. So we want to try to do the same that we do forward, doing it backwards, so to derive a detailed chronology of the events that predated the birth of the sun. So we know that the solar system matter was built by many generations of stars. So we know that helium and hydrogen, they were built during the Big Bang, but then everything else from carbon to lead, etc., was instead made in stars. So we have that many generations of stars, hundreds to thousands of stars during the presolar history of the galaxy. They contributed a little bit by little bit to build up the carbon, the oxygen, everything that we have. So we know that at some point the matter that ended up in the solar system ended up in a star forming region, a molecular cloud, and then in this molecular cloud it was isolated from more contribution from stars, and then stars formed in this cloud, including the solar system. So we have identified two different T1 that we can try to measure. One is what I call the isolation time. So the time from when this molecular cloud was isolated from additional contribution from stars, but we could also instead try to measure what was the last star that added matter to the solar system. I will explain in a bit more detail how we do this. So first, the isolation time. How can we measure the isolation time? So we have T0 is the time when the sun formed. N0, I show you we have because people can measure it in meteorites. Then we have T1, which I define as this isolation time. We need N1, because then by comparing N1 to N0, we can derive T1 minus T0. So what is this N1? To derive this, we have to try to analyze how the abundance of these radioactive nuclei change in the galaxy. This is actually quite easy again, because the rate of change in the galaxy of these nuclei will be due to a term that destroys them, because of course they keep on decaying, but also stars produce them. So we have a stellar production rate here, because stars produce all the elements, they produce all the nuclei, so of course they produce some of these nuclei as well. This is a nice equation, because the more of these you produce, and the more you decay them. So there is a point where the change goes to a steady state, the n over the t goes to 0, and so we can derive N1 at this steady state to be simply the production rate divided lambda. So in the galaxy with time, we will have an increase at the beginning, and then we reach this steady state value. So if this is the time when the sun formed, there is a point, the time of the isolation, where we scrap this term from this equation, and we only have the decay rate left. So the radioactive nucleus will only decay in the solar system matter, and so we can, by comparing N1 and N0, we can derive T1 and T0. Quite easy. This is what the people have done for a long time. But we have a problem with this, because the production of stars is not continuous. Here I'm putting an dp over dt as if star continuously in time, they keep on producing this nuclei. But star, they don't die continuously. We have discrete events. So there is a problem here. So what we can introduce is a delta. It's called delta, which is a recurrence time between the stellar production events. By very simple analysis, one can derive that this could be something between 10 and 100 million years. So if the decay rate of the nucleus we're looking at is much longer than this time between the events, then we're still fine with this formula, because between the events, the nucleus will not decay. So this is still okay. But unfortunately, this is not the situation for most of the nuclei that I'm looking at. For most of the nuclei that I'm looking at, we either have something like this, because the decay time is much shorter than the time between the events. So you see the picture is completely changed. We have a first event at 1 delta, where we produce a lot of this nucleus, but then before the next event, it's all completely gone. And so we have a peak, and then this decay decrease. Then at 2 delta, we have another event, so we have another peak, and then it again decreases to almost 0. So what can we do in this time? We cannot measure an isolation time, but we can still measure the last of this event that contributed to the solar system matter. Say we have n of these events, so we have at some point the last event. This is my time 1 now, and here is n1, how much I produced. If the solar system was born at t0 here, again, I can compare n1 and n2 and measure this difference in time from the last event. So in this case, the formula is even easier. I just take my star, I see how much it produced, and then I have the abundance n1. Very simple. Unfortunately, it's still a little bit more annoying, because often the delta and the decay time are similar. So in this case, I get a bit of a combination. So I get a peak of an event, then I get a decay, but I don't decay to 0 before the next event. So I have a situation more like this, but again, I can solve it with an analytical formula, because I can get that after the last event, I still have the production of the last event, which is this 1, but then I just have to have a sum term, which luckily converges to quite of a simple formula, and this is just the memory of all the events that happened before. So again, I can still solve the problem. And again, I can have an n1, I can have an n0, take the logarithm, multiply by tau, and I get the difference in time. So this is a bit the framework that we've been using to derive these differences in time. So what I've done specifically, from the list of nuclei that I showed you before, I focused on the first 4 on the list. And why I choose these 4 nuclei? There are 3 reasons for that. One reason is that you see that the half-lives are quite similar. This means that I can use them to measure similar time differences. So I can be sensitive to similar time interval. So I can use these 4 nuclei to cross-check my results. The other reason is that out of these 4 nuclei, at least 2 of them, they're quite well known in the solar system. So I have very good constraints. I don't have a big error bar on N0, which is good. And the third reason is that you can see all these nuclei, they're heavy. They're all heavier than iron. Iron 6 is the heaviest of the iron isotope that has a relatively long half-life. So, but these ones, they all have more than 100 in mass. So these nuclei, they can only be produced by neutron captures in stars. And this is the topic that I've been working on for the past 20 years. So I can say I'm an expert on how we produce these nuclei in stars. So I thought I can try to use this expertise to solve some of these problems. So how do we produce these nuclei in stars? That's my question. Because if you remember from the previous slides, everything that I'm doing here is related to a production. I need to know how much I produce in stars to solve the equation here. That's the crucial part, and also one of the most uncertain, because it really depends on the models that I use. So how do we produce these nuclei? I don't know if you've seen this before. It's the chart of nuclei. It basically represents all the elements and nuclei that are in the universe. And the black boxes are stable nuclei. So basically what we do is we plot each nucleus as function of the number of protons, Z, and the number of neutrons that it has. So when I increase vertically, I change the element because I add 1 proton each box that I go up. But then I also have information on the number of neutrons, so the isotopes of each element. So here, of course, I start with hydrogen and helium. These are the 4 little boxes here. They have each 2 stable isotopes. Then I go to the region here of the CNO nuclei. You can see the 3 boxes here of the 3 oxygen stable isotopes. Then there's the region in between here with what we call intermediate mass elements like sodium, silicon, calcium, titanium, etc. And then you get to the ion region, iron, cobalt, nickel. So only up to here, I only got up to iron. After iron, I have a huge variety of more elements that are not as abundant in the solar system, but there's a lot of them. And these nuclei, they have really high number of protons. So iron has 26 protons already. When I go beyond iron, I get up to, so for example, lead has 82 protons. This means that this nucleus doesn't like to capture another proton to build up to the next elements, because there's a very strong Coulomb barrier that you have to bypass. So this just doesn't happen. What we can do, though, is to capture neutrons, because neutrons don't have a charge. So all the nuclei from iron up, they can only produce by capturing neutrons. And all the 4 isotopes that I showed you before, they're all located, as I already mentioned, beyond iron, okay? And we have other interesting elements beyond iron, like all the rare earth elements that make up all the smartphones that we have today. Lead, for example, of course, silver is around here, gold is here, uranium, etc. So in detail, how do we produce these nuclei by neutron captures? Let me zoom in this region here of the nuclei chart. And I can describe briefly that we have 2 main modes to produce these nuclei. It's still neutron captures, but it's 2 opposite ways. One is slow and one is rapid. So slow relative to what? It's slow relative to decay rates of unstable nuclei. For example, the S process, the slow process, is the green line here. Say I start from this nuclei here, tellurium-122. I capture a neutron. So in the nuclei chart, I move 1 step this way. This is stable. I can capture another neutron. I can capture another neutron, etc. But then when I reach tellurium-127, this is unstable. And in this case, the neutron density is low. So instead of capturing another neutron, it will decay. And so I basically follow this green line along the black boxes. For the rapid process, it's completely the opposite story. When I reach an unstable nucleus, I will continue capturing more and more neutrons I cannot even show you here because the neutron capture reaches far, far away from the black boxes. But then, when there's no more neutrons there, everything will decay back towards the black boxes because I produce extremely radioactive nuclei. So normally the R process is described by these diagonal arrows that follow this chain of decays, for example, from here to here to here to here, until I get to the last stable isotope. So I want to understand if the 4 nuclei that I'm interested in, are they produced by the S process or are they produced by the R process? And this is important because the two sites have the two processes are completely different site where they happen. For the S process, I don't need an explosive environment, just hydrostatic stars. They can do fine because I don't need a lot of neutrons. And we know very well that this happens in AGB stars because we observe S process elements in these stars for 60 years. So we know that the S process site is AGB stars. For the R process, there's still a big debate. It's one of the big questions. Where does it happen? People think that probably neutron star mergers. Of course, neutron stars have a lot of neutrons, so that's a good place to have a lot of neutron for the R process. Or maybe special supernovae. Not every supernova is able to do that. According to the model and the observation agree with this. Okay, so when I go back to my nuclei, you can see there's one of them here. There's my iodine-129, was one of the nucleus that I was interested in. And you can see straight away that it cannot be produced by the S process. Because with the S process, when I have iodine-127, I capture a neutron, I produce iodine-128, it decays in 25 minutes. There is no way that this nucleus in AGB stars can capture another neutron and produce iodine-129. This is impossible. So what we believe that this nucleus is produced only by the R process. So this is a nucleus that can only come from special supernova neutron star mergers. What about the others? So the iodine-129, we have already set R process. That's it, only one source. For the palladium-107, the palladium-107 is located both on the S process and on the R process path. So for this nucleus in particular, it can be produced by both processes. Then we have curium-247. This is again only R process because the S process stops here. Once I get here with the S process, then I get all alpha decays and I keep on cycling around here. I cannot go beyond bismuth, which is the last stable isotope here. So this is again our process. What about hafnium-182? This is the big problem. So this is again a section of the nuclei chart. It's just a different graphic, but again we have the number of protons here. So we're moving from hafnium to tantalum to tungsten, and here is the neutron number. So we have all the different isotopes. And these gray boxes, they're stable nuclei. Can I produce hafnium-182? Which process should I use to produce it? Well, in the S process, I start from hafnium-180, I capture a neutron, I get to hafnium-181. Now, the crucial question is, what is this hafnium-181 going to do? Is it going to decay, or is it going to capture a neutron? That's the crucial question. The point is that on Earth, when the temperature is low, this nucleus decays in 42 days. So there are situations in AGB stars where the neutron density is high enough, say 10 to the 11, where it could capture a neutron and produce hafnium-182. However, we have a problem here, because hafnium-181 is a bit of a special nucleus. Well, nuclei, they're a bit like atoms. You're probably more familiar with atoms. They have energy levels. And these energy levels, they can be excited when the temperature is high. For the hafnium-182, here is the most simple energy level schematic diagram you could draw, but this is the states I want to focus on. There's a ground state, and there's a state here at 68 keV. It's pretty low temperature. It's pretty low energy. So people thought, when the temperature is typical S-process temperature, 200 million degrees, you can actually populate this 68 keV state, and this 68 keV state has a decay rate into tantalum-181 which is faster than the ground state. So what actually happens, or people thought, that this half-life is not 42 days, it's 3 hours in AGB stars when I have the S process. So 3 hours, S process, no, this doesn't happen. In 3 hours, it is much faster for hafnium-181 to decay into the tantalum-181 than to capture hafnium-182. So the standard picture was hafnium-182 is also an R process nucleus. We have to make it with the R process. We cannot do it in AGB stars. But then there was a big problem with this picture, because if we take the last R process event that contributed to the solar system, and we try to time when it happened, we get very inconsistent times. If we use iodine-129, it's about 100 years, 100 billion years. And the iodine-129 is well known, within 10%. So this is 100 million years, and it is consistent with the curium-247, which is definitely our process. We don't know it as well in the solar system, but these are consistent. Then if we take hafnium-182 from the last R process event, the timing is about 60 million years. And people have looked at all the uncertainties. There is no way that these can cross within uncertainties. So this was a big problem since the 1990s, when for the first time people observed the hafnium-182. So in the past 25 years, people have tried to find solutions to this problem. And basically they came up with two different ideas. One that was mostly the group of Wasserberg et al. Was to say, well, maybe we're thinking too simple about the R process. Maybe there's different R processes. There's an R process that produces iodine-129, but then stops and doesn't produce the heaviest. There's another R process that doesn't produce hafnium-129 and produces, iodine-129 and produces hafnium-182. But this was very controversial, because people who do R process models, they were saying, look, you can't do that. We're trying changing our free parameters in all the models. We cannot just block it in this way. Also, when the curium came up, and the curium is in agreement with the iodine, but is beyond the hafnium, then it would be difficult to produce up to that, then skip some nuclei, and then go to produce the heaviest. The other idea was that, okay, forget about the R process. Hafnium-182 did not come from this R process. The last process event was about 100 million years ago. Most of the hafnium from that event had disappeared. But then there was a supernova nearby the solar system that produced hafnium-182, not because of the R process, but because of some other specific nucleosynthesis events like neutron bursts that don't contribute to a lot of the abundances of the heavy elements in the solar system, but can produce specific isotopes. So I was interested into exploring a little bit more this idea, using the most updated input from the nuclear physics, but I am more an expert in AGB stars, so I needed to work with someone who does supernova models. And that's when I got in touch with Alex Seger, because he world expert on doing supernova nucleosynthesis. And at the time, he just moved to Monash University. So we decided this was an interesting project that we could work in together. So the idea was, okay, let's have another good look at this Hafnium-181. Let's put the latest nuclear physics information we have on this nucleus and see what happens in the supernova model, if they actually can produce it to explain the solar system abundance. Then we were lucky, we had it was the summertime in Australia, we had a really good student working with us for the summer. But then we're both not nuclear physics experts. We also need someone who can help us to calculate the decay rates of these nuclei. So we asked help from Stefan Gorieli. So I started looking at this problem, and I wanted to get the latest information about this Hafnium-182, the level structure, the angular momentum of this level, the energy, the decay rates, and all that. And to do that, you can look at the internet, of course, because there are very good databases on nuclear structure. And I looked at the three most famous of these internet resources. One is the International Atomic Energy Agency.